All right, let's jump right in. Today, we're taking the absolute most cutting-edge, brain-meltingly dense academic machine learning research and translating it into something that actually matters, the real-world, everyday human problems it's solving right now. If you're fascinated by how artificial intelligence is finally stepping out of the theoretical realm and directly into our daily lives, well, you're in exactly the right place. Today is entirely focused on AI's applied uses.
To pull this off, we've gone ahead and done the heavy lifting for you. We've combed through hundreds of incredibly dense papers from 6 major 2026 global conferences. We're talking leading symposiums on parsimony, bias and multimodal AI, lifelong learning, dynamics and control, learning theory, and causal learning. I mean, that is a massive amount of high-level math, but we've successfully boiled the whole shebang down to its absolute most tangible, real-world applications.
And this perfectly captures the core challenge we're tackling today. Think about it. An algorithm might work flawlessly in a static lab environment, right? Surrounded by controlled, meticulously clean data. But to actually help society, it has to survive the real world. And let's be honest, the real world is chaotic. It's full of noisy data, constantly shifting environments, and highly unpredictable humans.
So, to make sense of all this breakthrough science, our Lab to Life tour is going to guide you through exactly how AI is healing us, powering our physical systems, fixing media bias, and continuously adapting to our future. We've grouped these breakthroughs by the actual industries they're transforming right this second.
Okay, Section 1, From Lab to Real World. Let's see exactly how we translate theoretical math into actual human impact.
When you look at the proceedings from these conferences, you're hit with these wildly intimidating titles, like Physics-Informed Neural Operators for Cardiac Electrophysiology by Hannah Leiden and her team. Sounds intense, right? But what does that actually mean for us? Well, it translates directly into vital medical tools, like dynamically mapping the complex electrical activity of your very own heart. That's the bridge we're crossing today.
Which brings us to Section 2, Healing with Machine Learning. Let's step across that bridge and into the healthcare sector, which is literally seeing a massive wave of these applied AI technologies.
Now, before we look at the specific papers, it's absolutely crucial to grasp a concept called causal learning. This was a huge focus at the 2026 Causal Learning and Reasoning Conference. Basically, it's a technique that's finally moving AI away from just guessing patterns or finding basic correlations to actually understanding why something happens. If you're a doctor, you don't just want an algorithm guessing that 2 symptoms often show up together. You need to know for sure if one symptom is actually causing the other.
And the sheer diversity of where this is being applied is staggering. Researchers across these conferences are tackling everything from brainwaves to lungs. For example, Yifei Zhu's team is using AI to simulate alternate what-if scenarios in chest x-rays. This helps doctors make vastly better decisions without ever putting a patient at risk. Combine that with the cardiac mapping we just talked about, and it's a total full-body transformation driven by data.
Let's get even more specific. Over at the Conference on Parsimony and Learning, Isaiah Essien and his team proved something incredibly cool. You don't always need massive, power-hungry deep learning models to save lives. They tested lightweight models against massive, state-of-the-art architectures and found that these lean, parsimonious algorithms can successfully detect seizures. The human impact? It's huge. It means we can take life-saving algorithms and run them directly on something as simple as your everyday smartwatch.
Building on that causal learning we just talked about, Stella Dimitsaki and her colleagues introduced a brilliant framework for pharmacovigilance. They essentially used causal machine learning to sift through oceans of electronic health records to definitively identify drug-induced acute kidney injuries. It's an amazing example of taking passive, boring hospital data and turning it into an active bodyguard for patients, flagging dangerous drug side effects way before they can escalate.
All right, Section 3, Powering Robots and Physical Systems. Stepping away from the human body for a minute, let's look at how AI is optimizing our physical infrastructure.
Think about the energy grid. At the Learning for Dynamics and Control Conference, Apurva Thanivarntry's research showed exactly how end-to-end learning algorithms can optimize massive energy distribution. They improve what's known as aggregate flexibility. What does that mean in plain English? Well, when millions of us get home from work and plug in our electric cars at the exact same time, this AI works behind the scenes to prevent the grid from completely melting down. It balances the load seamlessly.
And in the world of robotics, Annie Chen's paper from the Lifelong Learning Conference on single-life robot deployment is just a massive game changer. Usually, if a robot hits a snag in a brand new environment, it fails, and you literally have to take it all the way back to the lab to retrain it. But Chen's research allows the robot to modify its behavior on the fly, out in the real world. Basically, it learns from its mistakes on the job, exactly like a human employee would.
Moving on to Section 4, fixing media and information bias. We all know AI models and social platforms deeply dictate our media consumption right now. So let's look at how researchers are structurally and mathematically fixing the flow of information.
Taking a totally objective look at network dynamics, Niccolo Paganin and his team presented some fascinating stuff at the Dynamics and Control Conference. They outlined a strict mathematical control approach to structurally mitigate the spread of misinformation across social networks. The cool part? They aren't looking at the messy politics of the posts. They're treating the spread of misinformation as a dynamic systems problem, using pure math to put the brakes on harmful falsehoods.
Along those same lines, impartial research by Tongtong Khan, Shufeng Hu, and their teams takes a hard look at the actual humans training these models. Their research reveals that the cultural backgrounds and personal risk preferences of the humans labeling the data accidentally introduce systemic flaws into the models. Basically, our human biases get baked right into the AI. But here's the good news. Because researchers have finally identified this mathematically, they can actively work to repair it.
Section 5. Smarter and safer continuous adaptation. The big takeaway across all these conferences is that algorithms simply can't be deployed and then forgotten about. They have to continuously adapt.
And that brings us to lifelong learning. This is the foundational concept ensuring that as software and environments inevitably update, the AI doesn't suddenly suffer from what researchers call catastrophic forgetting. Yeah, that's a real term. It's basically the ability of a system to learn a brand new task without mysteriously wiping its memory of how to do the last one.
We actually see this applied to consumer tech all the time. It's what keeps your phone running smoothly. Its operating systems constantly update behind the scenes. We also see it in super efficient video editing tools that can instantly adapt to new formats without needing massive, expensive server farms to retrain themselves. The AI is just continually learning to control diverse devices completely seamlessly.
Section 6. What will AI solve next? Which brings us right to the horizon of this research.
I want to share a quote from Yufsin Bai's paper at the Dynamics and Control Conference that beautifully captures why this whole explainer matters. The paper talks about the optimal control of the future via prospective learning with control. If we strip away the dense academic phrasing, the ultimate goal of all these complex models, whether they're parsimonious, causal, or lifelong, is simply to give us better, safer control over the outcomes of our own future.
So as you digest everything we've covered today, I want to leave you with a thought. Take a look around your own workplace, your industry, or even just your living room. With thousands of brilliant minds out there bridging the gap between theoretical math and applied science, what unseen algorithm is being trained in a lab today to optimize, protect, or totally elevate your daily life tomorrow? Thanks for learning with me today, and keep asking those big questions.